Yes, ma'am, we are ready to go.
Yeah, go ahead.
A very good morning to one and all present here. Imagine with all your mind, believe with all your heart, achieve with all your might. With this inspiring quote in this pleasant morning, we welcome you all for our today's session on MEMS Sensor Design by Dr. A.R. Kalaiarasi, Associate Professor, Savitha Engineering College, Chennai, as a part of our 2-week certification course on MEMS, organized by Center for Micro Nano Design and Fabrication, CMNDF, in association with Department of Electronics and Communication Engineering, Savitha Engineering College. Over to Ms. T. Archana, ma'am.
Thank you, Nancy, ma'am. A pleasant morning to everyone. Hope I am audible. Now, I would like to share a glimpse of our college and department. Savitha Engineering College, established in the year 2001, an autonomous institution which follows the Finland-based education model. And we march towards this smooth concept. Our college makes the students job ready by providing the industry 4.0 ready curriculum which imparts 21st century skills. Project-based learning integrated with subject improves the student skill set and makes our learners to be the best, which is the motto of our college. The Department of ECE was established in the year 2001. Our vision is to develop the department into a state-of-art in electronics and communication engineering education and pair with global standards. The Department of ECE has well-experienced faculty of proven ability and diverse specialization. The faculty actively involves themselves in a research in the field of robotics, VLSI, MEMS, image processing, and embedded system. Now, I would like to share about CMNDF, the Center for Micro Nano Design and Fabrication. CMN 2012 that brings the computer researchers working on an integrated circuit and system on chip design to create smart micro and nano system. Lab associate CMNDFR, Savitha MEMS Design Center, Wet Lab, Microfluidics Lab, Prototype Processing Lab, and Nanosynthesis Lab. Under CMNDF, nearly 25 papers were published in reputed journals and organized international conferences and workshops in collaboration with the Department of ECE, Savitha Engineering College. Presently, 4 members pursuing PhD under CMNDF, and our team includes 10 researchers from various disciplines who focus to work with the innovative thinking to bring up the groundbreaking achievements in the field of microfluidics, healthcare, and energy harvesting. Thank you. Now the session is handed over to Nancy, ma'am.
Thank you, Archana, ma'am. Now I would request Mr. G. Dinesh Ram, Project Associate, Savitha Engineering College, to introduce our guest of the day. Please, sir.
Yes, ma'am. Good morning, everyone. My name is Dinesh Ram, working as Project Associate in the Department of ECE, Savitha Engineering College. It is my great pleasure to invite our today's chief guest, Dr. A.R. Kalaiarasi. She is currently working as Associate Professor in the Department of Electronics and Instrumentation Engineering, Savitha Engineering College, Chennai. She has practical experience in MEMS simulation tools like IntelliSuite, COMSOL, and Coventrover. She has fabricated cantilever beams, microgripper, electrothermal actuator, and capacity sensors at Indian Institute of Science, Bangalore. She has published more than 25 papers in reputed journals and conferences in the area of MEMS. Her research area includes control system and MEMS. We thank you, ma'am, for accepting our invitation to give us your valuable talk on MEMS sensor design, and we welcome you once again. Now I hand over the session to Dr. A.R. Kalaiarasi, ma'am. Please, ma'am.
Thank you, Dinesh. Now we'll move on to the presentation. First, I would like to present what is today's schedule or what I'm planning to do. I would like to share a screen. I hope my voice is audible to the audience.
Yes, ma'am.
Today's schedule is design of MEMS-based pressure sensor. Actually, in this title, I have given as a piezoresistive pressure sensor, but with time promise, I'm going to start with the capacitive pressure sensor. Then I'm going to uh, show the simulation of the piezoresistive pressure sensor. And the software which I have chosen is going to be Console. Console is the microphysics software, and almost all the MEMS-based software is based on FEM, that is finite element method or finite element analysis. So today's schedule is going to be just I would like to introduce you about the basics of pressure sensor. Then directly I will go on to the console environment, and there I am going to show you the demonstration, or from the scratch I'm going to tell you where to start and how to start using the console software. Okay. The pressure sensor. The pressure sensor is a device which is going to sense the pressure, and it's going to convert the measured pressure into an electrical signal, and its magnitude depends upon the applied pressure. Okay, there are many types of sensing principles are available. As I already mentioned, capacitive, using capacitive method, we can able to sense the pressure, or we can able to convert the pressure measured into an electrical signal. I can use a capacitive approach. That is, two plates are going to be there. One plate is going to be a fixed one, other plate is going to be a movable one. And the movable plate is going to be called as a diaphragm, and which is going to be very thin in structure. And then if the pressure is applied, that movable plate or the diaphragm undergoes deflection. Because of the deflection, the gap between the two plates is going to change, which results in change in capacitance. If I'm using here visual circuit, if I could be able to measure the change in capacitance, then I'll be back calibrating, or I'll be doing the signal processing using a visual circuit, and I can able to convert the pressure into an electric voltage. Then if I could back calibrate the electrical voltage directly, I can able to relate what is the pressure input and what is the corresponding electrical voltage. And here important point is the pressure sensor is a successfully fabricated MEMS device, which is also commercialized one. Okay, so that is an important point here. Then the sensing principles, capacitive can be one method, and piezoresistive is going to be the next method. And these are all the two methods which we are going to look today. Then this is just what I explained, which is showed by means of the diagram, the applied pressure, because the beginners who is going to be new to MEMS or new to MEMS software or MEMS design, this is going to be the approach. So where to start? You have to start with a journal paper, and you have to clear about the basic equations. Maybe a pressure sensor, it may be a very simple device, doesn't matter. You have to be very much confident about your basic equations, governing equations, because the user should not rely only on the simulation, because simulation is one of the two. So you can measure, or you can do some simulation, and you can get some result. But how to validate the result, that is very important. Even for UG level or PG or PhD level, definitely you have to validate it. So for validation, before going for fabrication, because obviously fabrication is going to be a very difficult one, and getting your fabrication facilities or fabricating the MEMS devices. I'm not talking about meso devices. Meso, in the sense that is millimeter scale, we can able to fabricate it. But for the micro scale or in nano scale, definitely we have to the next after the simulation or along with the simulation, we have to be comfortable with the basic equation. Okay, so you have to rely on some journal papers, or we have to rely with some MEMS-based book also. Okay, so the fundamental equation is very important, and how fundamentally the device is working is the next important one. That is explained in this slide. Then these are all the, as I already mentioned, these are all the governing equations. The governing equations are as important as our simulation, because this is going to give an check, or this is going to give an idea. Yes, I'm doing my simulation properly. Yes, I'm getting some results. This is comparable with the analytical equations or the governing equations. And as I already mentioned, the sensing methods, piezoresistance and capacitance. And the fundamental equation for capacitance is nothing but F over A by G. And both the things are shown here in the slide. So the first one is piezoresistive phase one, and actually here it's a cross-sectional view. So this is shown with only a two piezoresistors. Actually, will be maybe called as a off-Wheatstone circuit, which is the electronic circuit, because always the MEMS device has to be incorporated with the electronic circuit. Then only it's going to be a complete MEMS device, or otherwise it's going to be either, then only we can call it as either a MEMS sensor or MEMS actuator. Otherwise, it's just off a completed. Okay, so MEMS plus the electronic circuit, that is integrated circuit. Then when it's going to give you a complete picture of the fabricated MEMS device. Then the second part is the capacitive based sensing. So that is also shown. I already explained you. Then here today's objective is we are going to design a capacitive based pressure sensor. Then we are going to design a piezoresistive pressure sensor. I'll be using PMMA or any other diaphragm because I'm going to start from scratch. So that's up to you and me one day. So which material we are going to use, and I'm going to do the simulation in COMSOL. COMSOL, as I already mentioned, this is the FEA or FEM based software, and we are going to analyze the performance of the pressure sensor. For that, note that is using the equation. I'm not going to go you using the equations and all, because if once the equation is given, people are smart enough to calculate the values. So I'm just presenting my results, okay, for analytical values, and I'll be doing the comparisons, right? Now we'll be moving to the COMSOL simulation. I stop this presentation now. Now we'll move on to the COMSOL. I already opened one. This is the COMSOL 4.2. Actually, regarding the license and all, we can request the COMSOL people. We can able to get the 1 month student evaluation license, or we have to give some money and we have to purchase the COMSOL. These are all only the two methods. So this is going to be the view of the COMSOL. So first beginning is going to be this one, right? I have started from the scratch. Even I have not saved the name. I just started from the scratch. This is the model builder, model resort. So I'm going to use the 3D builder. So 3D. So we are having so many phase dimensions: 3D, 2D, 1D. We use 2D symmetric. 2D symmetric in the sense in one dimension. That is why is it. Any one of the dimension is equal, then there is no, if x and y is going to be the same, then no need to go for both x and y. We can factor and we can use just x and z dimensions. That is the meaning. Okay. And axis symmetric is going to be for a cylindrical kind of structures. So this is after using COMSOL or after using any FEM based software or MEMS based software, you can get an idea. So the next step, so first we have to choose the dimension. So I'm going to choose 3D. Then you have to click this next button. Then we have to add physics, and all this actually all softwares in one way or other way it's going to include the physics. In COMSOL, it's directly given as physics. Okay.
Ma'am, excuse me, ma'am.
Ah.
Sorry for the interruption, ma'am. Are you sharing any screen, ma'am? We are not able to view.
Wonderful. I'll share this.
Okay.
Yes. Now it's visible. Actually, I thought it. Sorry.
Yeah, ma'am. We are able to see. Thank you.
Again, I will just recollect what I have explained. So this is going to be the screen, and I have started from the scratch, as I told. So this is untitled .mph. MPH is stitched, and this is the screen how it is going to look. Then the next is the model wizard. Model wizard, and go back because the audience missed the screen. So this is going to be the first screen. That is the space dimension. Okay, so here we are having 3D, 2D axisymmetric, 2D, as I already mentioned. What about the things which is visible or which is relevant, not visible, which is relevant for your structure? You have to choose the dimension, and basic drawing knowledge is enough. Or if you are well versed in CAD and all, then within a matter of a day or one day or 2 days, you can able to start your simulations and using any MEMS software. And if you don't know CAD, also don't worry. Basic engineering drawing knowledge is more than enough, but we have to sit and we have to work. So that is the important thing. Okay, so 3D, I'm going to choose 3D. Then the next is here I have to add the physics. So I'm going to use the electrostatics and solid mechanics because the physics and this is that's why I mentioned clearly in the beginning itself. The basic of the device must be known to you. The basic understanding of the device is very important. So without that knowledge, if you're proceeding with the simulation is ridiculous. Okay. So I know that I'm going to design a capacitive pressure sensor. So I will be applying some pressure. So then there is going to be a change in capacitance. So I need both the solid mechanics and then electrostatics. So I'm going to add the solid mechanics physics. Then I'm going to add the electrostatic physics. You have to select both this thing or one by one also you can select. Then you click the next button. Just press this plus symbol or right click also. You can take the plus symbol. You have to add this. It will take time because I have added two physics certificates. Now, this is added. So electrostatic you can see in the bottom of the middle of this window. Electrostatics and thermal mechanics is added. Then the next is automatically it will go to next. Automatically in the sense this next symbol, arrow symbol, if you are going to press, it will go to the steady type. The steady type simply I'm going to use the stationary steady, right? Then I'm going to click this flag symbol in order to finish. Okay. So next we have to choose the length unit. I'm going to choose micrometer. The degrees I'm not going to change. Let it be in degrees itself. Then on the left side of the model builder, the geometry is there. And I'm going to start with the geometry. Geometry, you just click geometry and right click it, and then you can able to see blocks, cones, cylinders, sphere, and more primitives. You can able to see the user more you can. So, basic engineering drawing knowledge and having the knowledge of the coordinates, you can able to build your structure. That is going to be very important. Okay, any of the MEMS topic, maybe Cometra there or maybe IntelliSwitch, the three important things is one is your geometry. The geometry should be perfect. Okay, perfect in the sense in x dimension, that is in xy dimension or in the planar dimension or in the z dimension. Okay, that is very important. The geometry should be proper. Then the materials should be proper. Material properties must be proper. Then the boundary conditions. Okay, the name may be different for different sources, but actually now we are going to discuss about console. So I'll be using the same word, the boundary conditions, that is the governing equations, or in other words, the governing equation. If all three, geometry, material properties, and boundary conditions, is going to be perfect, then you can able to get a proper result. Then you can rely on the result. Okay, this is important. So using the basic knowledge, we can able to draw the diagram. Now this is the beginning session, so I will be using a simple structure only. I'm going to use block. Then I'll be using some dimension. I'll be using 400, then 400, and this is going to be the substrate. Okay, for the substrate, I'll be using some 40 micron thickness. Then you have to click build select. In this blue side, you can able to see the structure, the block which is created, and you can use the zoom extend and zoom selected, and actually the zoom extend and go to default 3D view is going to be these two keys will be using regularly. Okay, these two are important. Then only we can able to get the idea whether I am creating a proper 3D structure. Okay, then I'll be going to, this is going to act as my substrate. Okay, what is my idea is the substrate is going to be there. On top of the substrate, I'm going to place an dielectric medium, and then on top of the dielectric medium, I'm going to place a diaphragm. Okay, that's a very simple structure. Then again, geometry, block. Then for this dielectric medium, I'll be using a simple structure, the same 400. Length and width is going to be 400, 400. But the thickness and be using the 10 micron. We can change. Later also we can change. There is no fixed rule. Always we have to be uh, concerned about the dimensions. But later we can change, but it will take time. So again, build selected. Actually, I have not mentioned the position. That's why it is not done properly. So I have to. I just want to keep this dielectric medium on top of the substrate. So my set position is going to be 40 microns. So now you can see, right? 40 micron. So again, I'll show you. So the block one, then selected, right click the first block. The second which is having a length and width is 400, 400. Then height is 10. Then the position is going to be 40 micron because my substrate is already having the 40 micron. On top of that one, this go and switch. So that's it. So this is the second one, and the third one. If you want a circular diaphragm also, we can able to create. I already done that. Like for easy understanding, I am going to use just a block. Rectangular diaphragm is also will do this. Okay, block. And diaphragm in the sense it's going to have a very smaller thickness. So this is just 20 microns. The same 400, 400 by 400, and 10 or 20 microns. Actually, when fabricating in the 20 micron device is not validated one, or it is not going to withstand the pressure at all after fabrication. That's why we'll be using more than 50 microns or minimum 50 microns. But this is just for simulation. That's why I'm showing you the height of 20 micron. And this exit position is going to be 40 plus, what is the previous one? 40 plus 10, so 50 exit position. I'm not changing any other position. Okay. So now all the three, that is the bottom plate, top plate, and then intermediate dielectric medium is also done. Okay. Then you have to use this zoom extend and go to default 3D. Then the next one is form union. Then the or. Then we go on for to the materials. Right click materials, open material browser. Then I'm going to give silicon for the bottom and top one, and intermediate I'll be using as a row. Okay, whatever the material you can search here, and even you can create your own material. That option is also available, but you have to supply the basic properties and advanced properties of the material. You have to search with the journal paper and you have to go with them. So in MEMS, because I already know that, or otherwise you can put in the search box and you can get the materials. So I'm going to use semiconductor, silicon. Actually, an advanced version of conservator, so many materials are available. Anyhow, for piezo resistor, I'm going to show you that. This is a basic one, and this is somewhat easy concept the point two. Okay, silicon. Then we can right click, add material to the model. Okay, by default, all the three blocks is going to be shown here, and I have to choose one more material, and be searching here SiO2. Already I have chosen, that's why it is there. Or otherwise, we go to MEMS, insulators, SiO2, right click, and plus symbol. Or on the top of this material cruiser also, we are having the plus symbol or the same only, right? So bottom and top plate is going to be silicon, and the second block I have to remove. So I am removing from selection. Then I say go to, just go to the geometry and then click it and right click, it will add automatically. Okay, just you have to go to the geometry, click it, click and then right click, it will add it to the material, right? And we have to check with the material properties whether all material properties are given. If it is not shown, actually here you can able to see one cross symbol. If the cross symbol is there, actually it is not here. If something is missing in the sense the cross symbol is present here, then that is indicating you there is some property is missing in the material. So you have to go to this material contents and you have to type the values here. For example, epsilon if you want to change, or if I'm going to, I'll show this for silicon, if I'm going to change instead of 170 e power 9, that is 170 GPA in model, if I'm going to change 169 for my silicon, it's going to be 169 in the sense. I can go and I can change here. Okay, 169 GPA. Because that and all is going to be an important point, then only we can able to match our results with the analytical knowledge. So just click here. So my MEMS model is changed. If you don't want to change, if you want to proceed as it is, then you can proceed. Doesn't matter. Then SiO2 is the, I'm not going to change anything with the SiO2. Let it be. Then, so first what we have completed is geometry is done. A simple structure, very simple structure from the scratch. It has been started and it has been drawn. Then we started with the materials properties also. How to change, I explained you. And a new material also you can able to choose. For new material and all, you have to just again click material and right click. And material, if you are going to click material, it will go and ask. So here you have to go and include the properties. Okay, material contents. The basic properties we are going to add, you can create your own material. Okay, now I'm not going to use this. So I'm deleting this. And the next one is the boundary conditions. That is the governing equations and the boundary conditions of the given model. Okay, so which is going to be where I'm going to apply the pressure, which is going to be a fixed one, which is going to be a mobile one. Mobile one is going to be default, so I am going to concentrate only on the fixed one. Okay, so I'm starting with the solid mechanics. You have to right click this. Then already what we have done is the domain. Okay, boundary conditions or this that has to be given only to the boundaries, not to the domain. That's an important one. And slightly there is some differences in potential or in so, but finally any design or any device which is going to be created in any one of the software is going to give the same results, provided if you are going to do it properly. So I'm going to, in solid mechanics or structural mechanics, is mainly with the mechanical properties of the device, right? So I know that this is a, without this definitely the device is not going to work. So a fixed constraint, I have to give a fixed constraint. The fixed constraint I'm going to give to the four sides of the diagram. So just click it and right click, you can add it to the boundary selection. So just rotate and right click. Rotate. I hope you can able to see this. Rotate and right click. And again for the default view, zoom extend and go to 3D default view. Okay, so this is going to be my fixed constraint. And how I know this is going to be fixed in the sense with the knowledge. Okay, you have to study about the pressure sensor and if we have some fabrication knowledge or lens knowledge, you can able to we will be getting the same knowledge. Doesn't matter. Then I have to apply some pressure because this is a pressure sensor. So again, solid mechanics. So what I have to choose? Here we having, I'm going to apply a load, so a boundary load. I already mentioned always the 3D dimension, the structure is going to be 3D, then the boundary conditions is going to be in 2D. And if the structure itself is going to be a 2D and the boundary condition is going to be in 1D. Okay, this is some uh, custom you have to make it in your mind, or you have to be. This is the software they are following it, right? Boundary load. Then I'm going to apply the pressure here, and I can right click it. Then what is the value of pressure I'm going to give? And here, that is in the mid of the boundary load, we can able to see load defined as force per unit area, total force, pressure. I'm going to use pressure. So its unit is Pascal. Pascal. I'm going to give some 10,000 or 20,000 Pascal, 20 kilopascal. So I have to use either 20 e power 3 or 20,000. So 20 e power 3 pascal. So these units in the we can't change. So you have to adjust. If suppose GPA 1 GPA you have to apply in the sense accordingly you have to calculate 1 e power 9 you have to give here. Instead if you are going to give 1 that is nothing but 1 pascal. So that those things you have to be very careful while doing the simulation. Right? So boundary load is given. Then again I'm going to electrostatics. Electrostatics. Here electrostatics I am going to just use. I'm going to use it for the calculate the capacitance. Okay, changing capacitance. So electrostatic. For that I have to apply the excitation voltage. So for excitation voltage we are having ground and electric potential, and electric potential in the sense if I'm going to choose electric potential I have to use some mathematical equation and then integration. Then only I can able to get the capacitance. Instead, console is giving a terminal, and automatically we can able to calculate the capacitance. So I'm going to choose terminal, right? The terminal in the sense where I'm going to apply the voltage. So I'm going to choose the top voltage. Right click, and here in the bottom of this terminal type, I'm not going to apply charge. Instead, I'm going to apply voltage. So I have given voltage, let it be. It is just an excitation voltage. So let it be 1 volt. Right? So again, electrostatic because ground I have to choose now. Electrostatics, ground. Then the bottom of the substrate I'm going to apply as a ground. Right? There is no need to supply any value to the ground. Okay. So we completed geometry, material, boundary conditions. And one more important is these three are in the hand of the designer. That's why I told we have to be very careful about this geometry, material, and boundary conditions. But the boundary condition is very, very important, much important, very much. Okay.
Excuse me,
Then,
ma'am.
yes.
Participants are saying that your voice is breaking, ma'am. So, can you please adjust your microphone, ma'am?
So again, I have to repeat.
And this one, this last 5 minutes portion alone.
Last 5 minutes.
Thank you.
Okay. Terminal. So again, I'll explaining you regarding the electrostatic boundary conditions. Electrostatic boundary conditions, we have to choose either here, right click it. Again, we have this is for excitation. Okay, so I have to choose here electric potential or electric potential in the sense as I already mentioned. I have to use some integrated integration. Then only I can able to find my capacitance. That console is providing one more option, which is called as terminal. Using this terminal, we can, if I'm going to, we can apply the voltage. And using this terminal, just by using a simple expression, I can able to calculate my capacitance. Okay, so that's why we are choosing terminal. And electric potential also, if you want, you can take the electric potential and you can apply the electric potential. But it will take some more time to calculate what is the capacitance. Okay, so you have to click this terminal. Already have to created terminal 1. Then next is right click, then ground. So actually I have created 2 terminals and 2 ground. That is not required. So I'm going to delete this one. Just for understanding, I have created again. Okay. So terminal 1, we have to, I have chosen the top plate of the top diagram, top side of the diagram. And then the default voltage is 1 volt, and let it be because this is just an excitation. So I have just given a 1 volt. Then ground, I have chosen the bottom of the substrate, and for ground there is no need to keep any voltage. Okay, by default it's going to take it as a 0 volt. So the boundary conditions has been given. So the geometry is completed, material is completed, and boundary conditions are very simple because the section. So that's why I'm choosing a very simple structure. All the 3 is completed, and all the 3 is going to be with the hand of the design. That's why I already told these 3 are very important. Then the next is the mesh. Okay, the beginners, it is a very good advice. They have to just go with the mesh, which is mesh option, which is available in the console itself. Okay, after getting some experience, and after suppose your device is very complicated one, which is having a very smaller dimension, maybe a 2 micrometer, and one side of the one part of your device is going to be an 500 micron or maybe 1 millimeter. These much of differences are there. Okay, the same device is going to have 1 micron mm and as small as 2 micrometer, because lesser than 2 micrometer is not fabricated at all. Even fabricating 2 micron is also a very difficult one. Okay, for an example, I have taken as 2 micrometer, right? So if your seeing device is going to have a structure of 1 mm structure and 2 mm structure in the same device, right? A part is going to have 1 mm. In that kind of thing, definitely the normal machine is going to, because that is going to consider only the 2 micrometer dimension, and the normal machine is going to mesh all the devices with a 2 micrometer or lesser than 2 micrometer. Meshing in the sense dividing the device into smaller module or smaller mesh. Okay, uh, that is the basis of finite element method. That's why I have told you FM is going to be the basic for any of the MEMS based software. Okay, even if you go with the ANSYS, so this is going to be the FM is the basic one. So finite element method. Yes, and I'm going to divide it into smaller mesh. Okay. Then if that kind of structure is there, then we have to go with the other kind of meshes. So many meshes are there. We can use the symmetrical meshes and moving mesh. So many meshes are available in console. But if you are a beginner, then go with the console default model based meshes. So this is the mesh, and right click it and physics control mesh, and the element size is normal because here the geometry which I have shown is a normal geometry only. Okay, it is not going to have a smaller structure. It is a normal basic structure. So I go with the normal element size. Okay, so just you can either right click the mesh and you can give the build all, or you can click in the model settings window also. One build all icon is going to be there. You can click that also. This is nothing but meshing. Okay, this is called as a mesh, and all these terminals are called as nodes. If you want to get some idea, you have to go with the any basic FEM. After getting some FEM knowledge, if you are coming for the simulation, then it will be good. Okay, for a normal devices, we can able to do the meshing as I already mentioned. But if it is a complicated device, as I mentioned earlier, then definitely you should get some knowledge. You should have some knowledge of meshing. Then that definitely that is going to help you, right? And how many elements are there? That is also shown here. That is 5,000. That is around 6,000 elements are here. Okay, 6,000 elements. If the elements is going to be more than 1 lakh, and definitely your computer is going to be not at all going to solve the problem. So these be sure whether how many elements are present here. Okay, otherwise you have to do some changes in the geometry itself, right? The geometry itself in the sense either instead of 3D structure you can go with the 2D axisymmetric or just 2D. Okay, 2D in the sense I can make Z direction itself, so I can reduce the number of elements in the directions. Okay, tetrahedral is not required. Normal surface measure is enough for me. Okay, that kind of knowledge is very much important in order to get, yeah, in order to do a proper simulation. Okay, so 6,000 elements are here. Then they have to go with the steady, steady, right click, complete. It will take some time. You can able to see here. This is doing the, it is solving the problem. So that's why it is showing here. This is completed. Uh, by default, console is going to give. So actually, the geometry, material, boundary conditions, and all pre-processing. And solving that is steady is going to be solving the problem. Then the results section is called as post processing. Okay, these three are very important in any frame-based software. So post process, in the post processing, the console is going to give some basic or default graphs. If you want, you can change. I'll show you how to change it out. Okay, what is shown here is the electric potential, what is the voltage they have applied, that is shown here, nothing more than that. And multi-slice option, which is already available in console. This is the default. And now I would like to see what is happening. I have applied some pressure now. So I would like to see what is the stress. Okay. So you have to click in the left hand side. In the left hand side, you have to click the stress, and then after that, you'll be having the surface, and in the surface, you can able in the middle of this window, you can able to see solid misses. This is nothing but one misses stress. Okay, the pressure is applied. What is happening to my diagram? How much deformation my diagram undergoes? Right? That is that you can able to understand from the one misses stress, and the unit is Newton per meter square. Then, if you want to change or if you want to see a new result in the sense, you have to click result, right click result, then 3D plot group. Then you can right click 3D plot group. I'm going to check with the, again I'll go with the surface. You have to play with this. Okay, so many options are there, arrow and multi-slice, isosurface, so many things are there. Just it is going to do differently. That is. Then here, replace expression. Okay, I hope what audience can able to see this, right? So replace expression, solid mechanics, because here only I am going to have my displacement. I know that because it's a mechanical problem. Total displacement, then the unit is going to be in micrometer. Then click this plot. Yes. This is going to be my deformation, that is total displacement. I'm going to take this here. Yes, 3.357 into 10 power minus 4 micrometer. If the properties are, because I have not changed my properties in all, so I'm getting the, I have not changed any material properties, so that's why I'm getting this. And if you want to see the deformation also, because this is just shown with the color changing, if you want to see with the deformation, that is also possible here. Surface, deformation, right? You can adjust the scale factor. Now you can able to see here, and you can adjust the scale factor. Based on that, you can able to see here. You can adjust this because already this is 86,000 something. If you want to change to 1 lakh, right? So you can change this. This is just post processing, just to view the results or present the results. Okay. Then you can able to do a 2D plot and a 1D plot. So many options are available. Now we'll move on to the electrostatics. I just want to measure what is my capacitance. Already the voltage is there. Now we will change the pressure, or I'll show you how to do the parameterized speed. Okay, that we will do. Then we will want to how to calculate the capacitance. For parameter, you have to go to the lower. That is previously I have just given only a 20,000 or 20 kilopascal. Now I'm going to vary the pressure from 10,000 pascal to 10 kPa to some 15 kPa with steps of 1000 pascal. And I'm going to check what is happening to my diagram. Okay. So for that you have to use the global definition parameters. Then in the name you have to apply. Just give the name P naught. Then value. The first value will be 10,000, right? Description, apply pressure. Right. Actually, I have not saved the design. If you want, you can save this. Then you have to go to the steady. I'm going to add one more steady because in the same stationary step also we can add the parameterized speed, or we can go with a separate. That is up to the designer only. So I'm going to add the another steady. Add steady. The same stationary. In stationary only we are going to have the parameterized speed. This is steady to. Okay. Then right click steady to parametric sweep. So here we have to use the parameter values range. We have to keep the range. So select this range. Start with applying zero pressure is not right kind of thing. So I have started with 10,000. So let's go to start with the 15,000. Then step maybe 30, just 5 values. Whatever values you want, you can give here. But if you according to the number of values, it's going to take one. That is the difference. So this, okay. And parameter name I have to input here. Add. Okay. So now I'm going to for the steady one, I just do the like this. Steady to the in boundary condition also I have to change because already I have given some 20 power 3. Here I have to apply. Suppose if I'm going to give it wrongly, then it will indicate in red color. You able to see, or after completing, it will show the error. Okay, let me check or confirm whether I have used the same name, parameter name. I have used the same parameter name. Yes, I have used the same P naught as my parameter. Okay, so steady to the now it's going to solve it for 5 values, so it's going to take some time, some more time. Okay, the default plot of the electric potential, that's why it is showing the same plot. Let's move on to the stress. You can able to see here P naught of 6 is 15,000, right? So phase 1. And we can convert it into a video, that is also possible. Layout, go to take all this and frame number of frames is 6, because of the 6 values starting from 10,000 to 15,000. So we can convert it into a and time also we can able to change. Display each frame for 0.1 second is the default, so you give some 10 seconds. It is also given. You can able to see the, you are going to play this. You can able to see 10 seconds. I have changed the time as 10 seconds now, that's why it's taking 10 seconds time. 11,000. If you want, you can play with the time. And for stress, I have shown here. Similarly, we can able to see the deformation. That's going to be a beautiful view, because the deformation we can able to view properly and we can able to understand. Yes, if the applied pressure is going to change, the deformation is also going to change. Okay. 14,000. Then the next is right. So I have given repeat, so I have to stop this. I'll stop this. Now we'll move on to the capacitance calculation. For this, we have to take some time, or I'll close this and I'll work on one more, doesn't matter. Oh, my screen is not visible. Everyone, I have to share.
The screen is visible, ma'am.
Visible only, no? Okay. Now I'm getting some messages here, that's why I'm asking. Put this stop, then we'll move on to the capacitance calculation. Because the capacitance I'll be getting in this window, the right side, bottom of this. So only I can able to see this. Okay. So how I'm going to do is, just go with the derived values, right click, global evaluation. Then in the expression, you have to choose electrostatics, capacitance, then symbol is going to be there. Physical symbol, and we have to get this capacitance 1.8 into e power minus 30 farad. So this way you have to calculate the capacitance. And now we will move on. I hope the capacitance, capacity pressure sensor simulation we able to understand. Then we move on to the piezoresistor. If you are having any doubt in capacitance, later we'll discuss. I close this window and I share the other window. Just a minute. Give me a minute. Because COMSOL multiphysics 5.5 or higher versions are only having the piezoresistive physics. That's why I'm changing my application to the newer version. Once it is open, I will share the screen. It's not opening. And actually, I have not mentioned how to save. This is just like that our other Windows application files, how we are saving in Word or in Microsoft Excel. Similarly, we can go to the file window and it can save. Okay, it's not new. I'm using both the console multiple steps, it's taking time. But we have to console multiple 5.5 is opening. Let it open. I will explain you about the piezoresistive pressure sensor. Meanwhile, share that screen. Again, we will move on to the PowerPoint slideshow because it's taking some time to open console 5.5. Okay, then move on to the piezoresistive pressure sensor. So we'll be keeping the piezoresistor where we are having the higher stress. Okay, that is an important point we have to keep in your mind while designing the piezoresistor pressure sensor. And piezoresistor materials will be using either silicon silicon is a piezoresistor or polycrystalline silicon. We can use it as a piezoresistors. Okay. Then this is going to be the top view of the sensing unit. The same structure only I have created in console 5.5. I'll show you. Then how it is going to work is if the pressure is applied, the deformation occurs on the diagram, and then the deformation results in change of resistance of the piezoresistors, and the change in resistance is going to be measured through Wheatstone bridge, and the potential difference is going to be measured. So this is going to be the operation. Okay. And this is already known to you. This is the Wheatstone circuit and analytical calculation. As I already mentioned, this is very important. Okay, I'll be showing. I don't have time to solve all these equations, but I have already. One of my students has completed this alone, so we are having the values. I will share with you. Right. And what are the materials the student used this PMMA, these are the silicon and of copper. But for my design, I have changed these are the resistors system I use connecting on copper diaphragm instruments. Okay, the simulation. This is going to be the diaphragm. Diaphragm sure. This is also a 5 micron or 10 micron thickness. Then the stress analysis already we have done this one, and this is the piezo resistor dimension, right? Single piezo resistor. Similarly, 4 piezo resistors we are going to place, and then we are going to connect using a copper connectors, and this is going to be the structure. This is taken from console model only. I will check. Everything is open. My console is also open already. But anyhow, we will complete this and we will go on to the console 5.5. The same structure I have recreated in the console. And the displacement we will have seen. And this is for this value is not going to comparable with our shown demonstration. So the disk capacitor sensor and the material is different, geometry is different. Okay. But for this one, for the given dimensions, the given dimension of the piezo resistor, this is going to be the displacement. Right? We'll move on to the console now. Now I'm sharing console multiphysics 5.5. I have already done this because now we are running out of time. So I will show them. Already built one. I will show that one. Here, what are the changes? I already told you. The first thing, we have to start with the dimension. That is going to be 3D. The space dimension is going to be 3D. That is not changed. Then the next is the structure. Structure dimension is going to change here. That's almost same value, 400 microns by 400 by 400 into 10 micron is going to be the structure. Here, I have already done this. This is slightly, because this is a newer version, so this is having a slightly different view you're able to see. And here you have the component. Okay, once if you're familiar with any one version, even if it is 3.5, you can able to do it with the higher versions with some period of time. Okay, without much difficulty. So component, because I already done my research enrolled in 4.2 only, but now I am comfortable with 5.5 also. The geometry is there, the same 3D plane only I have used. Then the materials I have changed with N silicon and P silicon. Then the same physics only I will be using, right? And physics here, the physics is going to be different. The physics which we are have to use must be a piezo-resistive. Okay. If you want, you can make a note, solid mechanics. Then we have to use the piezo-resistive. So if you are going to right click, add physics. It will create a new window. This. So piezo-resistivity, this is not available there. That's why I am add to component to directly we can add and we can run the simulation as we already mentioned. The other things remain same, only the boundary condition is going to differ. Okay. The structure you can able to see here. Show the machine's material and all. So this is silicon. That is bottom plate and the top membrane is going to be silicon. And then silicon is the piezoresistors and the connecting arms I have changed. And if you want the connecting arms to change it into copper, that is also possible. Okay, I have done so many simulations. Okay, this is the final one. Then we move on to the. So this is 5.5. You are having so many recent options or so many options are available here. Piezoresistor, piezoelectric, and it is somewhat easy. You can able to apply. You can able to run your console file as an application window. That is also possible here. Okay. We'll move on to the presentation. So, in piezoresistor pressure sensor, so this is going to be the displacement screen. After this, we can able to capture the window and we can able to show it as your PowerPoint presentation, or you can use it for your thesis, something else, right? Then for the pressure applied, so 10 to 50, we have to calculate it. Actually, I have uh, shown it in the console window itself. We have to use these values. You can either you can take the values as a table, or you can manually you can note down the values and you can use your Excel in order to do this graph and all. Okay, actually, we'll be doing the graph in Excel only, right? So that is somewhat easy. Then this is the change in resistance. The piezoresistors. So what is the change in resistivity? That is shown here. The color change in resistivity, ohm per meter. And voltage distribution. For piezoresistivity, for the excitation, I have applied 5 volt, 0 volt and 5 volt. And output voltage analysis. For the applied pressure, what is the voltage difference in the Wheatstone bridge? That is shown here. And sensitivity, as I already mentioned, we have to calculate the sensitivity using this equation. The sensitivity equation is del V by del V. Del V is the change in output voltage and del V is the change in pressure. And we have to calculate what is the change in pressure and what is the change in voltage. Then that is going to be equal to 0.78 meters per kPa. So the conclusion is the pressure range is limited to 0 to 40 kPa for better sensitivity and linearity. The displacement linearly varies with the pressure that is shown in the graph itself. Okay. So this is varying with the and both the values, that is simulation and analytical, both have been done here. Okay. That's why I told you it's always better to use both analytical and simulation. So the difference, definitely the difference is going to be there, but at least it should match with the simulation, should match with the analytical, because analytical formulas is not going to change. That is good. So if there is any problem in the sense, there definitely that is going to be in our simulation while designing. That is, I already told you, know, the geometry or material or in the boundary conditions, we would have done some mistakes. So that mistakes has to be cleared and that has to be corrected. Then only we can able to do our we can do the comparison with the analytical. So always don't rely only on your simulation. So you have to compare it with either with the fabricated results or with the analytical results. Fabrication definitely it's going to be difficult one. So analytical results we can do. Okay. We are going to check even my UG students or PG students, definitely they will do with the, for validation, they will go with the analytical calculations. So change in resistance, the conclusion, we want to the conclusion again. The displacement linearity varies with the pressure, and the sensitivity can be improved by proper placing of the piezoresistors in the high stress region. Already we placed it in the same stress region only, but proper placement can be done. More proper placement can be done. Okay, and for this, how it can be, okay, for the audience, I'm going giving some more thoughts. Suppose if you are able to access console or any of the MEMS software, you can do the resimulate the same piezoresistor or capacitance. For the capacitance, whatever change you can adopt this. We are already, I have done with the rectangular diagram, right? It just convert it into a circular diagram. Actually, I'm also have I done that simulation. It is with me. And similarly, you can also use the circular one. Okay, circular diagram, and you can change the material. Materials can be changed. Instead of your silicon, you can change with the PMMA, that is polymers can be replaced, or polycrystalline silicon can be used. Okay, and even for the substrate, you can change different substrates, how it is working. And substrate is just your, it's giving a mechanical prediction. But anyhow, you can change the diaphragm and material change, you can change, and you can check what is happening to your either capacitive pressure sensor or to the piezoresistor pressure sensor. Okay. Then the next is, so these kind of things can be, these kind of changes can be done for the simulation side, and corresponding analytical calculations can also be done. And you can compare both of these, whether the circular diagram is working fine or your rectangular is working fine, or any other diagram. Okay, we are having for your rectangular, circular, only three options are there. I am changing the material, changing the dimensions. Instead of 20 microns, if I'm going to go for a 10 micron, what is happening? Right? And that kind of changes can be done. The next is, okay, after completing simulation, and I have done with the enough with simulation, and I have completed with validated with what is it, analytical. Then the next thing is we can go with the fabrication. For fabrication, MEMS fabrication is difficult, or we can do with the other types of fabrication like 3D printing technology, and many of the colleges are offering 3D printing. Even our college is also offering. So that kind of thing, but you have to scale up your device. That is very important. Okay, because the 400 micron, 400 by 400 micron method, definitely this cannot be done with the 3D printing technology, up to my knowledge. So we have to scale up your device, and we can go with the 3D printing technology. And then we have to test the based on the application, because the testing is also closely related to the application where it is using your capacitive sensor, capacitive or piezoresistive pressure sensor. So that is also making sense, right? Okay. Any questions? Yes. Any questions?
Yes, ma'am. Thank you so much
Nancy,
for the wonderful session, ma'am.
okay. Whether I have to extend it or this is correct, ma'am? Timing is okay? Or still
Yes.
time is there?
No, you're on time, ma'am. You have
Okay.
kept your time.
Okay.
Okay. There are a few questions, ma'am.
Okay.
Let me just start with the first question. Which version of COMSOL is great for beginners?
4.28. Console 4.28. That would be better.
COMSOL
4.28.
Okay. Okay. The next question is, what is the importance of meshing? Is it possible to design localized surface plasmon resonance based sensor in COMSOL?
Meshing, without meshing, we can't do anything with the frame-based software. So definitely meshing is very much required, because all the equations, the governing equations, even it may be electrostatics or it may be any piezoresistive equation, that's going to be solved only for a single mesh. Then that is going to be continued, or that is going to be shared with the next node. So this is going to be the basic of how the frame-based software is going to work. So without meshing, we can't do anything in the frame-based software. And almost all the MEMS devices or MEMS softwares are based on frame-based software. So we can't avoid meshing. Meshing is very much important. Then that if you know that the device, the localized resonance sensor, okay. If you know the physics of the device, the governing equation of the device, dimensions of the device, of course materials, then definitely we can do the simulation in console. That is my answer.
Okay, ma'am. Can you please tell the commercially available pressure sensor, ma'am?
The MAP Motorola pressure sensor MAP is commercially available. You can able to see actually in my, I have taken the diagrams from that sensor only. It is available in the books also, MEMS book. SD Centuria's microsystem design and all. So that is an commercially available pressure sensor. MEMS based pressure sensor. In the sense the dimension is going to be in microns.
Okay, ma'am. The last question for this session, how to measure the maximum tolerable pressure so that this device won't break?
Right. Very good question. We have to come. Actually, I forget to tell that one. Actually, we have to, we use some materials, right? In my demonstration, I have used silicon. Right? Silicon yield strength is going to be there. Material property, we are going to check with that. So that is the reason why we check with the von Mises stress. And if the von Mises stress is lesser than the yield strength of the material, for example, silicon, then obviously your device will, or the fabricated device or your device will definitely withstand. Suppose your von Mises stress is greater than the yield strength of your material in the sense, definitely you have to change your design, or you have to change your dimension, or you have to change your material. This is the
Yeah, okay, ma'am. One more question from our participant side, ma'am.
okay.
Costa, sir, please.
Ma'am, good morning, ma'am.
Good morning.
Ma'am, ma'am, my question is actually in console multiphysics already some inbuilt materials are there, but beyond that, actually apart from that, if we want to add some kind of additional materials, is there any possibility or is there anything like to add those kind of materials, ma'am?
Yes, yes. I actually mentioned in my presentation itself, we can right click the material, then before going to the material browser, directly we can add the material if it's possible. If possible, it is there. But you have to, you should have the basic material properties. Console won't provide it. Okay. You can search with any
Okay, ma'am.
journal. You can search with any journal, because don't depend on the internet for that finding the material properties and all. Definitely, you have to search any journal and the properties are given. Then you can give the same material properties. It is there.
Okay, ma'am.
Only
Thank you.
two options
Thank
are
you,
right.
ma'am.
If
Thank you
you're
so
going to
much,
right
ma'am.
click, if you're going to right click, only two options are there. Either you have to browse it or you have to either choose new material. That's it. It's a simple one.
Okay. One last question,
Thank you,
ma'am.
ma'am.
Okay.
Polysilicon or silicon, which one is better for piezo resistor?
Polysilicon. Polysilicon now. Because I fabricated and I found polysilicon is better. It's giving some better results.
Okay. Thank you so much for your patience for answering all the questions, ma'am. Actually, our participants' expectation was to see something practically done. They were asking, they were longing for the simulation, and we have seen an excellent simulation of piezo-resistive pressure sensor by you today. Thank you so much for sparing your time with us. Hello.
It's not better. Thank you.
Okay, ma'am. Okay. Nancy?
Yes, ma'am. Thank you so much, Kalaiarasi ma'am, for accepting our invitation and for joining with us today. The session would have been useful to many. Thank you, ma'am. Yeah, participants, we would like to know about today's session feedback. So we will launch a poll now. Please do your voting for the questions asked so that we will take up your valuable suggestions, and which helps us to improve our upcoming sessions too. So we will launch a poll now, right now. Participants, kindly start your voting. Yeah.
We expect all the participants to be active during the poll. Out of 46, only 32 have answered. Please, all of you, post your poll so that we can get the actual feedback, and it will be very helpful for us in improving this further sessions. Attendees, please poll your thoughts. We would like to see your active participation, so kindly vote. Only 75% of the participants have voted. Yeah, Nancy will announce the results.
Okay, ma'am.
Anyways, it is good. Thank you so much for your voting. We'll try to improve your session, improve the forthcoming sessions as per your request. Nancy will finish up formally.
Okay. We thank all the participants for joining with us today. Hope you all would have gained knowledge about MEMS sensor design using COMSOL and would have been benefited by the session. So our upcoming session is on MEMS actuators by Dr. Shakti Swarup, Assistant Professor, Center for Nanotechnology Research, Vellore Institute of Technology, Chennai, scheduled on June 29th, coming Monday from 11 a.m. to 12:30 p.m. I repeat, our upcoming session is on MEMS actuators by Dr. Shakti Swarup, Assistant Professor, Center for Nanotechnology Research, Vellore Institute of Technology, Chennai, scheduled on June 29th, coming Monday from 11 a.m. to 12:30 p.m. We request all the faculties and students to attend this session and get benefited. Dear participants, this weekend we don't have any live sessions. Meanwhile, you can utilize the time by viewing all the informative videos which is uploaded in our Google Classroom. So the link for today's quiz will be posted in our WhatsApp and Telegram groups. We request all the participants to kindly finish the quiz of today's session before 11 p.m. today. So learning never exhausts the mind. With that note, we officially end our today's session. Enjoy the course and extend your fullest cooperation. So meet you all in our next session on Monday. Thank you all for your wonderful participation. Stay safe. Thank you.
I think we can end the meeting, Nancy.
Okay, ma'am.